All right, in this third system, now this is going to be a bit more quantitative of an example. We'll actually have a lot of numbers and it's more realistic. In fact, this is an example from the book on page 298 if you want to look. Gonna work through it, right? So you can like compare the work they do there to like how I work through these problems. So this is exactly this is actually example 17.3, page 298 in the book. And right, so it's a rack and pinion, and what this is it converts rotational motion to translational motion, right? As we rotate, well, you know, we got a few different components here. We rotate this bar, that ends up causing a rotation in this bar, that then rotates this bar, which is connected to this gear, so that gear is rotating, and in that sense we're converting this rotational motion over here to a linear motion as this gearing is turning the rack here. Now this diagram is going to get very complicated, so I don't want to make this too much, so I'm just going to do this words. This here is called the rack and the pinion. We're converting this rotational motion to up and down velocity through the teeth and the gears here, and the orientation. What we want to do is determine the speed of the rack here, right. So there's a lot going on. Let's see. Let's mark this up as we go along here. But we've already talked about the rotation that we know is going to occur. As a result of this rotation here, we'll get a similar, or not a similar, but we'll also get a rotation of the BC element. So let's just put this in here, and we're just putting everything in. So this is actually imposed. So this is actually negative, right? So maybe the first thing we do is put our coordinate system here, at least the IJK location. Let's just sneak it up here. Again, I'm just being careful, thinking ahead of what needs to go here. I, J, and then that out of the page direction is K. So that rotation at the right hand rule, wrap in the direction of the rotation. My thumb points into the page. So this is actually a negative rotation in terms of the coordinate system that we conveniently, by convenience put in there. But the rest of them we're gonna impose on the system in the assumed positive direction of the coordinate system. So that will be the assumed direction for omega BC, and then this is the assumed direction for omega, we'll call this omega CD since it connects pin C to pin D there. And right, okay, great. Let's just make a note of it so we have it in our notes and we have it in our work. Omega BC and omega CD assumed to be in positive k hat direction. Now, just looking at it, right, if that's rotating this way, actually this one will make sense, right? That should rotate that way. But if that rotates that way, right, and if we have this rotation there, maybe it makes more sense for this omega CD to be in the opposite direction, so the actual rotation here might be in the opposite direction. But again, oh, and by the way, right, this rotation will be the rotation about point C as well, or about point D, I mean, right, pin D there. So, yeah, I think we can sneak it in there, right? So there too is still omega CD because that's a rigid body, right? Being extra careful not to get in the way of later drawing, but I think it's actually it's going to be okay, right? A lot of these lengths are already on there. Okay, let's get into it now. So the first thing we're going to do to determine this, right, we're going to start from this known quantity over here and work our way through the system. So we're going to take element by element and apply our relative motion ideas here. Right, so this is, this is the first kind of real example of this relative velocities for this rotational motion associated with the rigid body kinematics that we're starting to analyze here. So let's take, let's analyze the velocity of point B for the AB element. Okay, that's how I'm just going to communicate with myself what I'm doing here, right? So I'm using the AB bar here to then try to get at what VB is, right? And so in doing that, we'll be having the absolute velocity of VB related to the absolute velocity of VA, and that's from the fixed coordinate system of like the ground here. Equals VA plus, and now here's that relative motion, omega AB crossed into the position vector of B with respect to A. So let's put that in there in our diagram. Starting from A, this is our position vector to get to B. So this is our B from A's perspective. Right? Okay. Now this is pinned. A is pinned. B is not pinned. Pinned to the ground, we should say, right? There's definitely a pin pinned to ground, and so that is 0. Okay. Let me put it there. Okay. There's tape there, so that's gonna smudge. See that? I've taped my problem statement on there, so I want to make sure it stays there forever. Okay. So pinned to ground. Now we need to talk about the the absolute velocity of B with respect to ground is just from this term, just from the rotation of the rigid body, where A and B are both on that same rigid body. And so we have a minus 10 k hat, and that's we already talked about how the 10 radian per second rotation of the AB bar is in the negative k hat direction. Our thumb points into the page when we rotate. Or it's a clockwise rotation, observe that. And now this position vector, right, to go from A to B is going to be 6 inches to the right, and how far do we go up? We go 10 inches up. Sorry, that's 12 inches up, right? That 10 was there for the radians per second. You got 12 inches going up. Okay, so we'll have 6I hat plus 12J hat, right? And then we do a quick check. K crossed into I is in the positive J direction. So this first term is K cross I is in the positive J term, but then it gets negative there. So this is going to be minus 60 J hat, right? Positive J from K cross I, but then we got a negative out front. And then K cross J, we have in the negative I hat direction, but the negative flips it around. So we'll have a positive 120 I hat. Okay, and that is the absolute velocity of point B, or pin B there. Great. That's good. So we're done with the AB bar. We've got, we've converted the information of the 10 radian per second rotation of AB to the absolute velocity of B. And now we can even put in there what the absolute velocity is, like a little add it to the picture. So if this is 120 in the I hat direction, and then 60 in the J hat direction, but negative, that means that we'll be going down and to the right, but more to the right. Okay, so down and to the right, but more to the right than we are going down. So the velocity of this point is going to look something like that. That's VB. Absolute velocity with respect to ground. Great. Okay. Now, let's see. Let's move on to the BC bar, and we'll use the information we now know about the velocity of B to get to the velocity at C using our BC rigid body. Okay, that BC rigid body has this relationship between those 2 points of absolute velocity of C is going to be the absolute velocity of B plus the rotation of the BC rigid body crossed into the position vector of C with respect to B. Going back up to our diagram, this is that relative position vector RC with respect to B, or as seen from the pin B. Okay, and then we do pretty much the same thing we did up here, except this is not 0 anymore. So this is going to be not 0 for the B. This is 120 I hat minus 60 J hat crossed into omega BC. That is not known. K hat, and that's why we assume it's in the positive K hat direction, just for consistency here. And then what's this position vector, right? We go over 16 inches in the I hat direction. So I know it's hidden there, but I'm going to put 16 I hat. This is just so I following along, not making any mistakes. And now here's where we're 12 inches is the whole height from A to B, and then the height from A to C is 10 inches. So we're actually dropping 2 inches in the j hat direction. Okay, so here I've already put it in there. I snuck it in there when it was off screen. 16 I hat minus 2 j hat, right? Okay, so then our VC is then going to be, let's see, we've got, where are all the I hats? Let's see, where do we get I hats? That's going to be, well, the 120, right? 120 I hat, and then the K cross J hat gives you a negative I hat, right? But then that's negative there. So K cross J is negative I hat with another negative, so we'll get a plus 2 omega BC from that cross product. And then we'll have two terms that are in the j hat component. One is negative 60 from right there, and the other one is the K cross I. That's a positive j hat, so we'll have a positive 16 omega BC j hat. Okay, great. So that is not as clean as we were able to get out of the analysis of the AB bar, and that's because there's another unknown we've entered, right? We're entering the system here, which is omega BC. Okay, now let's carry this forward, moving into the last rigid body here, which is the CD element. And what that is, right, it's a bar connected with the gear, but that's all rotating all together. And what we're going to actually do is hopefully get a relationship for VC using this. And how we're going to do this is why it's helpful is because D is now fixed, right? So that has absolute velocity of nothing, of 0. Okay, so we're going to have another relationship for VC, and then we'll be able to set these two things equal to each other, right? VC using the CD rigid body. Okay, so this is velocity at C is the velocity at D, that we know. Well, let's just write out the whole relationship. And then omega CD crossed into R of C with respect to D. This, again, like above for A, this is pinned to ground. Okay, pinned to our, fixed coordinate system here. So we'll cancel that out like we did for A, and then we need to put on our diagram what the position vector of C is with respect to D. Right, and that's this vector. That is our C from D's perspective. And so here we're going back. How far are we going back? We're going back, 6 inches, that's this quantity right there, to go from D to C, and we are going up the 10 inches, right? Okay. So we have this unknown omega CD in the k hat direction crossed into minus 6 in the I hat direction plus 10j in the j hat direction, up 10. To the left 6 and up 10. Okay, so with this we can say VC is minus 10 omega CD. Why is it minus 10? Because K cross J with the right-hand rule gives you minus I. And then K cross I is positive J. So we get another negative omega CD, but this is in the J hat direction. Okay, so now we have two relations for what the velocity at C is. Okay, and these both scale together, right? So we can at this point we could draw the velocity at C. It's going to be once we know what omega CD is, we at least know what the direction is, because omega CD could be positive or negative. Either way, it's going to be along a line that is more horizontal than vertical, and with like a positive slope. So the velocity of C at this point we can say is something, generally looking like this. But whether it goes that way or that way, we don't really know yet. But you can interpret it. If VB is moving down here, VC is probably going to be moving up, right? So it should be along that line, just from intuition. And so that means that we expect omega CD to be negative, right? And that the actual rotation of this element is actually, in the opposite direction. So let's put this in here. This is like what we expect, because I'm pretty confident in that. I'm also confident because I know what the final answers are, but pretend we're not cheating. So that is the velocity. See how this is getting complicated? In fact, now I need to update where this is. Omega CD is this curvy thing. Okay, and then the velocity vector there is VC. Okay. Excuse me. So I think we need a new sheet here, but the next step is going to set these two things equal to each other, and then we'll have there's actually two relationships here, right? There's the I components and the J components. We should be able to solve, when we set these two things equal to each other, those go away. We'll be able to solve for omega BC and omega CD, the two unknowns here, from the two equations which come from the two components. Okay? All right, so lost focus here. There we go. Okay, now, and that's because, let's spell this all out. Velocity at C is the same whether we're talking the BC element or the CD rigid body, right? So in the I hat direction, right, we get the relationship that 120 plus 2 omega BC, that's coming from the BC analysis we did, that equals minus 10 omega CD, that's from the CD analysis. And then in the other direction, in the vertical direction, we have a minus 60 plus 16 omega BC equals minus 6 omega CD. Two equations for the two unknowns. This should be solvable unless we have a rare occurrence of it being, not independent relationships. But that, right, if this represents the physical system there, we should be able to solve this. So let's start with, I think the easier one, well, it doesn't really much matter, but the fact that there's a 2 there and those are both even numbers, the I hat should be a good one to start with, right? You see how that'll make a nice relationship for omega BC in terms of the other one, because all we're going to do is divide by 2. So from that we can say omega BC is minus 5 omega CD when we divide by 2. Pull the negative 120 to the other side and divide by 2, so negative 60. Okay, so that's a nice linear, neat relationship. It's easy to plug into the other one. Okay, so then we have minus 60 plus 16, and now instead of omega BC we're going to plug it in. Minus 5 omega CD minus 60, that equals minus 6 omega CD. And let's see, so then let's pull all of the constants to the left side. So we have negative 60, but then we have a negative 16 times 60. Those two terms together give us negative 1020. And that must equal, and then we have negative 6 over here, but then we'll have a positive, what's 16 times 5? That's 30 plus 50, so 80. 80 minus 6 is going to be 74 omega CD. And then from that, we can solve for omega CD. Oh, here we go. We already determined that this should be negative, right? And that we said that that should be negative so that omega CD points in that direction, just from intuition that if VB is pointing down, C had better start going up as omega BC rotates this way, right? Omega BC should be positive, and then omega CD should be negative because it's rotating clockwise. This one's rotating counterclockwise. And that's what you get. You get clockwise for AB. That's pinned to something that's then rotating counterclockwise, which is pinned to something that's rotating clockwise, right? You get this back and forth alternating angular directions. Omega CD is at negative 13.78 rad per second. None of these are what we're actually determining as a final answer here. Omega BC here, we're just plugging it into our relationship that we found up here. Now that we know omega CD, it's going to be minus 5 minus 13.78 rad per second that we just determined for the CD rotation, minus 60. Excuse me. This is omega BC equals 8.92 rad per second positive, right? As we discussed is at least what my intuition was. Okay, so that's positive. Not as big. Excuse me. So now we move into our final analysis. And I actually need to go back to the original diagram here, which we need to add one more point on our diagram, because what we need to do is now relate it to the rack. So I'm going to put the point on the rack that's in current contact with the pinion, with the gear there. That's point R. And so what we're going to do here for this last stage is now relate point R, which is going to be its absolute velocity. You know, we want the absolute velocity of R, which could be anywhere. Any of these teeth will have the same absolute velocity from the fixed coordinate system of the ground. But we're going to relate that to point D, because that point that's in contact with both is going to have the same exact velocity. So the velocity there, the velocity of the rack is the velocity of the gear at that exact point, with both direction and magnitude. So we are going to write the motion of R with respect to D. So that vector right there is going to be the position vector of point R with respect to D. And what we're looking for is, and what we'll be solving for, is actually the velocity vector of that point, which is, you know, the exact as the entire macro scale rack. Okay, so I think this will be the last time I need the diagram, but we'll keep it handy just in case. Okay, now let's solve for, again, we needed really that to be able to solve this. Okay, so we have VR, this is also on the CD element, okay, because that's on the outer edge. So we have VR equals VD plus omega CD crossed into the position vector of R with respect to D, or as seen from D. This still is 0, nothing new there, still pinned to ground, still pinned to our fixed coordinate system. Okay, so then our VR is just going to be the cross product of this minus 1378 k hat that we determined up here as omega CD, crossed into 6 inches in the I hat direction. Let's not worry about units yet. We'll just turn that into the I hat vector. Okay, so RCD is perfectly horizontal to the right. And as you expect, right, K cross I is going to be in the J hat direction. K is up here. It's so hard to do this with the video. K is pointing up towards the video, wrapped in the horizontal, and my thumb points upward. So this is in the positive J direction, but then it's negative, so it actually, the velocity points down, which, you know, back to the diagram, we definitely expect to be true, right? The rack must either move straight up or down, and with this rotation, the rotation is actually in the negative sense, right, of the pinion. That should cause a downward velocity of the rack. Okay, so we have VR is then negative 82.7 inches per second are our units there, J hat. And that is the final, right? And so our speed here, VR, is 82.7 inches per second. I think that was just like, well, what? Oh yeah, that's because we determined velocity, but it actually asked for speed, right? Just determined VR, well, pretty, I think it's more descriptive to say this, but yeah, if we just want speed, it's 82.7 inches per second. All right, that's a good one. All right, so now we have a true example, right? I don't know, I've been living with these systems and examples. I think the systems are more like you can make general statements about how systems work. It's just an example of one of these types of systems. But, you know, they kind of been working through examples all along. And what we're in, right, we're examples of these like relative motions of these rigid bodies combined in these systems of really rigid bodies where, yeah, and then where the focus is on the velocities involved. Okay, so we have, in this example, a few, really two rigid bodies, and then there's some constraints on them, right? So A is pinned, C is a slider, B is, you know, a pinning between the two rods here. But right, so we have rod AB. We have a known rotation that's in the positive K direction. Let's put our coordinate system on there. This is a good place for it. I hat, J hat, K hat comes out at us. And so that's a positive omega AB of 5 rads per second. We want to determine the velocity of the collar, so what the velocity down here is. Now that's a slider, so it can only move that way. Let me see that. I think that's good. So that's the velocity of C that we're looking to solve for when the angle here is 60 degrees and the angle there is 45 degrees. Because now the C is just free to, it's not pinned to ground at all. It's not pinned to our fixed coordinate system, right? Okay. So we're going to start here, like, think about how we're going to do this, right? We're going to start here by using this known information to determine the velocity of B. We'll then use the known information of velocity of B through the rigid body BC to determine the velocity of C. Okay? All right. Velocity of B, it's not just velocity of B, using the AB rigid body. Velocity of B using the AB rigid body. And I'll make some more markups, I think, of this diagram as we go along here. We'll have to refer back to it. Okay, in terms of velocities, the velocity of B absolute with the ground is equal to the velocity of A plus the rotation of AB crossed into the relative position vector of B with respect to A. Okay, so that's, I'm not going to draw it, right, but that's this unit vector. And so that goes up an amount, right? And we've specified that AB is length 2 feet and B, okay, capital A, capital B, that bar has length 2, and capital B, capital C has length 2.5 feet. And then we, with specifying these angles, we should be able to work through the trig to determine what that position vector is. So let's actually work through that here, right? So this would be my representation of the position vector of BA. So really, this is point A down here, and this is point B in our diagram. And we want to know what these components of that vector are, where that is 45 degrees specified right here. Yeah. So, well, that's similar. All right, the triangle that we have here is where this is 2. That's the actual length, right? These are just like the magnitudes, right? I don't know, it's similar. I mean, it's the same triangle, right? This is 2, but here we're just drawing lengths, not thinking of them as vectors, is what I'm saying. 45 degrees, and so then this would be 2 cosine 45 degrees, and this is 2 sine 45 degrees. Okay, that's going to give us that. The other thing is this VA is 0 because that's pinned to ground. So all we have for VB, for the velocity of B, is the 5 radians per second rotation of the rigid body crossed into the position vector, which is 2 cosine 45 degrees I hat plus 2 sine 45 degrees j hat. And that is a position vector from A to B. So do the calculations. Let's see. Both cosine 45 and sine 45 are root 2 over 2, so that's the one angle where those are the exact same. So we should get the same magnitudes, same coefficients for the I hat and j hat, but which one's positive, which one's negative? Well, k cross I, that's k cross I is positive j, so the j hat component is positive, and then you do k cross j, that is k cross j, that is in the negative I hat direction, and so we have a negative I hat component there, right? And that's it. That's velocity at B, and so that's at a 45 degree angle. And we could add that to our diagram. So it heads backward and upward at a 45. Okay, so there is the velocity of B, where that is a 45 degree angle. And that's just imposed from the geometry and the fact that we're rotating at 5 radians per second. And really the direction doesn't get affected by 5 radians per second. It's just the magnitude will be how quickly it's moving in that direction. So the rotation, I mean, that makes sense, right? Okay, and it's really just, this is only valid, this direction is only valid for the snapshot when this is 45 degrees. As soon as that gets more than 45, right, the angle is going to turn more and more, or the direction of B is going to be more and more horizontal. Okay, but that's good for that snapshot. Now let's analyze the velocity of C, get to our answer here. Well, here we're going to use rigid body BC with our relative velocities, which says that the velocity of C is the velocity of B, which we now know, plus the rotation of the BC rigid body crossed into the position vector of C relative to B, as if B was the observer here. Okay, so now we'll do a kind of a similar picture what we did up here. Now we're going to have, well, I used the black dots, and C is down here. Okay, this is our position vector, RCB, and we're looking to get the components here, and we see they're both going to be negative. Okay, well, this triangle is 2.5 down and 2.5. And so, and then this angle that we're imposing here is, I probably drew it actually a little bit sharp, is 60 degrees. All right, so actually too big of an angle there. So then this is going to be the I hat component is going to be 2.5 cosine 60 degrees. But the actual vector is going to be negative, right? And then this is 2.5 sine of 60 degrees. The actual vector is negative as well in terms of the I hat, J hat components. Okay, so VC is definitely a little bit more complicated because of this. We have VC equaling the velocity of B relative to ground. This is the absolute velocity, 7.07 J hat, plus, am I going to be able to fit this in here? I don't think so, so I'm going to just do the plus down below it. The unknown omega BC, K hat, right, that we don't know. Oh, we need to add that, right? So we're going to assume it's in the positive K direction. That is this way. Which, right, if we're rotating this way, this is probably moving that way. So maybe that one is valid. I think that's going to be the correct direction, right? And here's an example where they're actually both in the same direction because we don't have two pin points. This is a slider allowing this one to move. If this was pinned to the ground as this rotated, right, then there's an even number of bars here, right? Okay, we have omega BC, that's unknown. K hat is the direction, crossed into 2.5 minus cosine 60 degrees I hat coming from the triangle, minus sine 60 degrees J hat. Okay, now by observation, or by imposition of the slider, we know that that VC is only in the I hat direction. So this left-hand side is so by observation of the slider, I guess it's not really observation, it's we're imposing it because there's a slider, but it's the slider, the bar there's oriented in the horizontal direction. We know that VC equals, well, some magnitude in the I hat direction, right? That's the speed, and then nothing in the J hat direction. Okay, so this equation with that imposition tells us that in the I hat direction, our equation is the velocity of C is minus 7.07. That comes from that term. And then which one of these is I hat? Well, that's K crossed into J. K crossed into J is negative I hat with another negative there. So we'll have a plus, and when you do the calculation, plus 2.165 omega BC. Okay, so maybe let's go in red here, we'll put the I hat components. It's this one together with that one, because we cross it with K. And then in the J hat direction, which we'll do in this bluer color, that's going to be this term and that term. J hat is going to be 0 equals positive 7.07 minus 1.25 omega BC, because K cross I is positive J, but then we got that negative there because the position vector actually has negative components. Okay, so we need to do both components here because in order to solve for the speed, which is what we need here at C, for the slider C, we need the rotation rate of the BC rigid body. So we can solve this for omega BC, which is 5.657. radians per second. And that's a useful quantity. Tells us that our assumed direction for omega BC is correct, which we said, yeah, that makes a lot of sense. And then we can go and plug this result into the I-hat equation, and we get the velocity. We get a speed of 5.176. Right, and you're just literally plugging that in there. You get 5.176 feet per second, all in the I-hat direction. Okay. Good. That's a good, nice one. A little bit more straightforward than that rack and pinion, which had another element associated with another rack. So really, two more elements. So this one's a little bit more straightforward, but gives you an idea of the types of problems we like to solve with these relative velocities for these rigid bodies.